So, quick recap of what we did last time is we went through the same basically shell balance, and we're starting chapter 3. So we went through the same shell balance. It's just that this time we did not assume steady state. So part of it was actually balance in time as well. So when we look at the small control volume, okay, what momentarily the rate of change of mass inside of that volume is basically what flows in through the boundaries or out, as the case might be. What is in, what is out? We decide on how are you oriented with respect to the normal to this volume. Typically you have to agree on what you're going to do. But typically when you have a volume, you typically state as normal the outward normal. Okay. But so to actually go inward, you actually have to go along negative of that normal to get inside. So essentially, when we kind of do that balance over the 6 sides of a cube in a Cartesian coordinate system, okay, I basically, rho is my density that travels with velocity v, okay, and that can get inside the volume only if it's strictly orthogonal to that side of the volume. Okay? Otherwise, all of the tangential components will flow past that volume and will not change the mass within the volume. And that's essentially the idea. So basically what's coming in through the boundary on the right side, we collect this component, and since normals have on those 2 sides 2 opposite signs, that's how that minus shows up in formulas, right? And I also have to, in this Cartesian coordinate system, since I'm taking coordinate vectors, when I dot or project my velocity onto coordinate vector in x direction, I get vx. Okay. If I was in the cylindrical coordinate system, I would get vr if I dotted it with delta r, right? So basically that's the definition of a coordinate system, right? When you do a dot product with the coordinate vector, you get the coordinate in that direction. So basically, what's coming in on the first side is basically rho v dot delta x, which is rho vx, evaluated at that side, which I call x. And then on the other boundary, I have the same thing just with the negative sign. And this negative sign comes from these normals being in opposite directions. And I'm evaluating at x plus delta x. Okay? So I do the same. I also have to, of course, multiply by the area of this little side, and in this particular case, it's delta y, delta z. So the first line is essentially my contribution through along x, and then I add contributions along y and z, and basically I'm done integrating, doing a surface integral over that box, or the box sides rather. And on the other side, I have this change in time of the mass, which is rho times v, right? Rho times velocity volume, delta x, delta y, delta z. Okay? So when I actually send delta x, delta y, and delta z to 0, so I shrink this to a point, I will get a differential equation at every point. And basically, I get d rho dt is minus divergence of rho v. And again, imprint this physical meaning of divergence into your brain. It's basically collecting contributions over surface of some small volume around the point, and then I'm kind of shrinking that point to 0 to get the differential version of divergence. So basically, if I had source terms, and so here I don't have any source terms or sink terms or anything that is creating or destroying my mass within this volume. If I did, they would be added to this. So this is just measuring what is physically going through the boundaries. And this is very typical. So divergence part is very typical part of any kind of conservation law. Okay? So if I'm conserving a quantity, the basic insight is this, that I'm going to change that quantity at a point or a small volume around the point only by flowing in and out of the boundaries of that volume. Okay? And adding any source and sink terms if I actually have them. But we're assuming no reactions or anything like that, so I don't have source or sink. Okay? So this is basically our equation of continuity. And then if I set my rho to a constant, okay, then I get my familiar form that divergence of velocity is equal to 0. So that's for incompressible fluids. Okay, so we had some writing things out. And then I repeat the similar thing for equation of motion. Of course, now I'm conserving something that is a vector quantity. So I'm going to get a vector set of equations, right? Because my mass is not a vector quantity, it's scalar. So basically, when I look at the momentum, my definition of Vxx is the x momentum that is traveling across x boundary. My definition of Vyx is x momentum traveling across y, and Vzx is x momentum traveling across z. So basically, it is this vector, Vxx, Vyx, and Vzx, that describes what happens to x momentum across all of the possible coordinate planes, okay, when I'm transferring. Okay? So my vector is describing the change of a vector quantity, so of that particular scalar quantity. So basically, when I actually do the change of rho Vx, which is my x momentum within this volume, okay, so this is my rate of change of rho Vx, is again what goes through the boundaries. But what goes through the boundaries is now quantified by basically divergence, okay, of this vector that describes what happens to x momentum across all the boundaries. Yes? So that's divergence of Vx, which is actually one column of my tensor phi. Okay? And I can also have momentum can be changed by the action of external forces. And that is quantified here. We call it gravity, but it could be in general some other forces. So when I repeat the same for y and z, okay, I will get 3 equations total. And basically my rho Vx, rho Vy, rho Vz, that is a vector. So I can write this as a d dt of rho V, right, on my left-hand side. And on my right-hand side, this is precisely why I define divergence of a tensor this way, so I can have a shorthand way to write this equation. Okay? It's not that some mathematician didn't have anything to do, so they came up with this first. Okay? It's that somebody needed a shorthand notation for that equation. So basically we can say, hey, my divergence of a vector is a scalar. If I have 3 vectors, I'm going to get 3 scalars, and that defines a vector. So divergence of a tensor is a vector with these 3 components. Okay? And I write that this way, and I put these brackets. This is the notation in the book to just remind you that this is a vector quantity. By the way, mathematicians never do that. They just like simplifying. They don't even like putting the vector sign. If they can omit it, they will omit everything. But then you don't know what is the beast that you're dealing with. Is it a scalar, vector, or a tensor? Okay, so basically we have then this shorthand notation. This is our equation of motion. And it looks small and compact and benign, but of course when we get to solving it, it can be trouble. So we quickly computed if I actually put this tensor and have pressure, 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 and zeros everywhere else, okay? Then I get the divergence of that is actually gradient of pressure, and that's our familiar term that we already kind of know from seeing this equation elsewhere, because this will simplify to Navier-Stokes. Okay? So basically, if I just leave only those forces on the right-hand side, we get the material. We will get the material to the material derivative now. So if I break down this phi, I'm going to have divergence of a shear stress tensor. Then I'm going to get gradient P and divergence of this rho EV, which is the convective component of the tensor, okay? Plus rho G. So let's just I have a claim here that this can be simplified and called a material derivative. And then what I'm left on the right-hand side is just action of the shear stress forces, pressure, and the outside forces. So this is my force term, and this is something like mass times acceleration in a very complicated terms. So let's get to that. So we're going to introduce material derivative. Oh, here we go again. Okay. I haven't rebooted my computer apparently in a long time. Except that I did, but never mind that. Let me try that glove, though. I think I tried it and it didn't work. Maybe a little better. It's gonna be fun. Same thing. I'm gonna do my best. Okay. So one thing that we have to recognize when observing any system, and sometimes it's going to be as simple as follows. If you're trying to measure, right, and you have flowing fluid, okay, your measurement device could be on, let's say that the flowing fluid is a river. Okay. Your measurement device could be flowing with the river on a boat. That boat could be literally just floating, going with the same velocity as the river. Or it could actually have its own motor, so going at a completely different speed. Or you could actually be standing on the bank of the river, and the river is just passing by, and your measurement device, let's say that you're measuring concentration of something, right, is just dipped into that one spot in the river. In those three cases, what you actually are measuring about the fluid is three different things. Because in all three cases, you're sampling a different portion of fluid and a different time in its history. So we have to recognize that, and we have to also recognize when we're modeling things, how am I going to discretize? Am I going to move with something, or am I going to be sitting on that bank of the river, right? And I have to adjust whatever equations I have. I can decide one system or the other. So far, we were actually keeping this, we were sitting on the bank of the river, right? And that's why we had that convected part, rho VV, flowing in. Right? But it could be that you can have a measurement that is flowing with the river. That's completely physical. So how are you going to relate the two? So we have to have a way to go in between the two. Because otherwise, your measurement is for something else, for some other fluid packet that is at a different distance than wherever it is that you're. So we have to be able to reconcile the two. So material derivative essentially helps doing that. So you could have that you could be in a static coordinate system. Or you could move with the fluid, right? Or move with some different velocity than a fluid. So what is actually most common to recognize in this river sort of parallel is either being static, just a fixed coordinate system, or moving actually with the river. Okay? In which case the observer is moving with the velocity v of the fluid, right? So our equations so far were essentially in this system, right? We're going to learn a little something of how do I go back and forth essentially with be moving with the fluid, but more general, we could move with a different velocity. So let's assume that this observation field, if you will, is F. Is my observation. And that could be temperature, concentration of something in the river. I might be concerned about phosphorus runoff from nearby fields or something of that sort, and I'm trying to measure something. Okay. So when I think about basically derivative of, normally I think about derivative, I go and do partial derivative in time of some x, y, z, t, right? I typically think about it as my derivative in time while my x, y, z is constant. And I don't write constant, but I'm going to write constant now because that's our assumption, right? With the assumption that x, y, z is not changing in time. But now assume that we're actually moving with the river. Then my position is actually a function of time because I'm moving with the river and the river is carrying me. So there's a strong correlation between where I'm at and so I have to take that into account, and if I'm doing a derivative, then I have to actually do a total derivative because all of these x, y, z's are also functions of time. So assuming that I actually have a trajectory, x, y, z, so that is observer trajectory. Then velocity of that observer, I'm going to do uppercase V of t, is dx dt, dy dt, and dz dt. And if I was drawing that trajectory, then it would be a tangent to that trajectory, right? Space. Then my total time derivative is actually, so I don't have just a partial derivative of f mathematically. If I'm actually looking at the derivative of my observation f in time, I have to look at the total derivative. And that total derivative in time as df dt, and that is ddt of f of x of t, y of t, z of t, t. And I have one too many of these. Have we gotten to this part in Kami's class, chain rule? If not, you've had it somewhere in your calculus 1, calculus 2. Calculus 2 must have been. So this is a partial derivative of f with respect to x, keeping everything constant, times dx dt, right? And then I repeat the same thing. So it's partial f partial x, keeping everything else constant, y, z, t constant, times dx dt. Plus I repeat the same for y coordinate, and I keep x, z, t constant, and partial f partial z, x, y, t, yes, dz dt. And then finally partial f partial t while keeping x, y, z constant. What can I recognize this first term as? First three. x, x, y, y, z, z looks like a dot product of two vectors. Which two vectors? Gradient. And again, the gradient, the actual gradient, mathematical gradient that keeps things constant at every single time, times dx dt, dy dt, dz dt, which is my velocity of the observer. Of the observer. So it's actually gradient f I'm just going to write this. Basically, each coordinate has all the other stuff kept constant. Dot v of t plus partial f partial t x, y, z. I haven't told you anything that you haven't known so far. So this is our chain rule. Now what we're going to introduce is say, hey, okay, now I'm going to recognize the special case when my observer is actually moving with the velocity. So this is actually velocity of a fluid. And I'm going to start looking at special cases where this F is something that I'm observing with the fluid, like density, something that I have in my equations already. So far, this was something general. So now I'm going to specialize this for the case of fluids. So in case B, v of t is actually velocity of the fluid. And in that case, I refer to this total derivative of f as material derivative. It's also called substantial derivative or hydrodynamic derivative. Okay? So in that case, df dt, and I have this uppercase d that you will see a lot in literature. It's partial f partial t plus v, velocity of the fluid, dot gradient of f. And that is material substantial or hydrodynamic derivative of f, of course. Are you successfully dealing with my beautiful handwriting?
What was the capital D again?
Huh? This is material, substantial, or hydrodynamic derivative of f is capital D f dt. So it's this special case of the total derivative of time where this trajectory that I'm actually taking the total derivative of is moving with the fluid. So normally I would just have dx dt, dy dt, dz dt for that trajectory, whatever the trajectory might be. But in the case that trajectory is actually fluid velocity, then I'm calling this total derivative, I'm calling it material derivative. I'm moving with the material, if that. Actually, I'd rather if the literature took off with hydrodynamic more commonly, but it's more commonly called material than hydrodynamic. Because hydrodynamic would click in my brain, oh yeah, I'm moving with the fluid. This material, when you tell me material, I'm thinking of solids, but okay. Hmm? It's just df dt is basically this in the case that I have this velocity being velocity of the fluid. So it's just the way we denote it. It's just the way we call it. So when you see capital D, it's referring to the material derivative. And it's assuming that you know that. We're not going to be terribly concerned about this because we have equation of motion in our forms that we can just apply. But this is, if you see the literature and you're required to actually translate between the two, you need to know that. So I have to give you that information. And it's good to actually see that basically equation of motion, however complicated it might look in a static coordinate system, when I move it to the coordinate system moving with the fluid or with the material, I'm actually going to get that form mass times acceleration equals to force, okay, which is useful for remembering. Okay, let's now move on and actually get to the equation of motion. So now we're going to actually apply this. And some of it you will have a joy of doing in your homework. Okay. So let's now actually look at the continuity equation. Then I know that my 0 equals to partial rho, my phi f is now rho, plus divergence of rho v. Now I'm going to use, so just like you have derivative of some two functions multiplied, you have a whole set of rules with this divergence or gradient applied to either a scalar dot vector or vector dot scalar or something of that sort. So I'm just going to actually state that rule, and you might get a homework to actually prove it. But there is a rule that says that this can be written down as, so I'm basically breaking down this term. Okay? So it's a divergence of a scalar function times a vector function. That is, so I take this operator and I look at the scalar. So this operator is divergence, but this nabla reminds me of a gradient. Okay? So it's actually gradient of rho dot v. So as if I took the derivative of the first one, but it's not derivative, it's gradient. Plus, then I keep the first one intact, and the second operator I apply to the v, so I apply divergence to v. Do you see the mnemonic? So it's kind of very similar to when I had a derivative ddx of fg, then I said it's df dx times g plus f dg dx. So it's kind of there's a parallel here. And this is why, frankly, I prefer this notation of divergence, because I have this similarity with the gradient, right? I could have just, there's notation where you, for gradient, you just write g grad, right? And for divergence, you write div, right? But then you don't see this. This is kind of, when you get into it, like you can easily write down then what this terms are. You just go down, it's like, what can I do with the nabla? For a density function, which is a scalar, I can do gradient of it. Right? And then you do dot, you transfer that dot v. Okay? So there is a visual parallel in the notation.
So you're able to distribute the gradient sign because one of the functions is a scalar?
Yeah, so one is scalar, one is vector, so that poses a problem. And you can actually prove this, but it's easy to remember actually that that's how it works. So you can actually go and see what's on the left-hand side, write it down, right? And then what's on the right-hand side, write it down, and see that it's actually equal.
So if they were both vectors, vector functions, you could not do this operation?
No,
Okay.
because then you would have VV, which is actually a tensor, right? So then you would have to do different things. Though there's some equality for that case as well.
So, the result of this operator is a scalar, right? So scalar plus scalar.
Correct, because divergence of a vector is scalar. So this is scalar, so that has to be scalar too. So that's also another thing you have to match, right? So it's an equality you can prove, right? And you will have a joy of doing that. Okay, so now I'm gonna can I recognize material derivative anyway? Anybody? Look at that, what you wrote for material derivative, and replace f with rho. So it's d rho dt plus rho divergence of v. So this is my continuity equation in terms of material derivative. So if I was writing equations for something moving with the fluid, this is what I would have to use. Okay? If I was measuring density and changing density, okay? So if I am measuring density as moving with the fluid, I have some little sensor that is moving with the fluid. Okay? Then what I'm measuring is material derivative in that coordinate system. Okay? And if I was translating it to some static coordinate system, I have to be able to go back and forth. So this is the equation that is true moving with the coordinate system, with the fluid. Okay, so this is my equation of continuity. Now we're gonna use a similar expression, just a little more, I need a little more complicated one for my equation of continuity. So I'm gonna first state some vector quantities. We need some, further equalities. The first one is that for any scalar function f, what we have is that rho df dt is equal to partial derivative with respect to t of rho f plus divergence of rho vf. So this is basically, if I look at the density times change, so this is my change of f, material derivative of f is change of f observed while moving with the fluid. And this is just my regular time derivative in my regular coordinate system. Okay. And this is sort of I have divergence. So it's my sort of net change of rho f by convective motion through the boundaries of some small volume, right? So this is net change of rho f by convective motion. So you can derive this if you actually take the equation of continuity and you write down what df dt is. Again, equation of continuity helps in deriving this. And more generally, if I actually have a vector quantity, then I'm going to have one more for vector, and that is rho d. This is the material derivative of a vector, so this is a vector equation, is d dt of rho now vector plus also divergence of rho vf. Now rho vf, this is a tensor, right? Just like rho vv was a tensor. So this in itself is a vector quantity as well. And f is some vector function. And this f was scalar. So if I wanted to write this down for f, this is just a general equation that is always valid. For f is vector field, of a velocity field. Then I have that rho dv dt, this is material derivative, this is acceleration moving with the fluid, as measured while moving with the fluid, is ddt of rho v plus my rho vv. And sorry if I killed you with these vector equalities, but this is precisely the one that we need to use. So when I look at I go back to my equation of motion. My equation of motion says d dt of rho v is equal to minus divergence of that tensor phi plus rho g. And this, when I break it down, I have the shear stress component. I have my pressure. Oops. Can I just write gradient of pressure? Do you remember that part? Divergence of that pressure times identity is gradient. Minus of rho vv and plus rho g. So when I take this and this and put it on the left-hand side, what do I get?
MaterialDerivative.
Yes? Do we see it in the line above? This plus this is rho dv dt. So this becomes plus on the left-hand side. Everybody's like, really? You had to do this on a Friday morning to figure that out? Please, it's the end of the week. Mass times acceleration equals to force. Shear forces, pressure gradient, outside gravity field. Yes? Good old Newton. So if I wake you up in the middle of the night, 2 a.m., and I write down equation of motion for you, you will be able to recognize it as MA is equal to F. We did not move away from Newton, did you notice? Good old Newton. He knew it all. He just maybe didn't write everything down in vector equations. Do we recognize? Again, this is the 3 types of forcing I have in the system. Shear forces, pressure forces, gravity, mother gravity. And on the other side, I have this. So if I'm actually moving with the fluid, I have MA is equal to F. It's just that I'm writing things down in the static coordinate system, and things are moving past me, and every time they're moving, I'm seeing a different packet of fluid. That's when things become ugly, right? And I have to have this rho VV term for the convection and whatnot. So that's why actually these equations become nonlinear and difficult to handle. I think that's plenty for like 2 minutes left. But
Dr. Brodovich?
yes.
So in the middle of the page, you described what 2 of the terms in the equation.
Yeah, so I'm really just using these 2. I'm stating them as facts. You can prove them.
Right.
And the way you prove these quantities, you simply go by definition. What is this by definition? What is this by definition? What is this by definition? You know how to do divergence of a tensor, right?
Right.
So you would go actually by, X, Y, Z and prove it. And one thing that you actually need to use in both of these when proving is the continuity equation.
Okay.
So that helps you shorten and kill some terms, essentially. Okay? So it's really just, it's algebra, or vector algebra, if you will. So it's a little tedious, so I'm not using the class time to do it. You're going to have your homework time to do it. Okay? So you will prove it to yourself. But overall, you can just, and I want you to prove a couple of them so that you can just get familiar with, like, okay, you pull a book, and in the back of the book, there's actually an entire set of these that you can just use. Okay. So it's not magic. It's just a little tedious. It's not magic. But it's helpful because I think for me, this is a very great, it's great insight that actually as you're moving with the fluid, you come back down to this mass times acceleration is force, which you normally don't see in the original version of the equation of motion. This is as tedious and hairy as we're going to get. We're going to start solving with this. So on Monday, we're going to state some special cases, Navier-Stokes being one of the most common ones. And then we're going to basically solve again our motion in our fluid in a cylindrical tube, just using this to see the difference. What is the difference when I'm solving the same problem using ready-to-go equations versus shell balance? And you will decide for yourself which one you like better, which one is more intuitive to you. Typically, these ready-to-go equations, they're good, but you arrive at the most complicated equation you could possibly have. Whereas if you're doing shell balance, you're kind of doing it layer by layer, and occasionally it's easier to integrate because you're doing it kind of step by step. So that's something in the back of your mind to be. It's good to have ready-to-go equations, but it's not always the easiest to solve. If you have a numerical solver, then sure. But if you're doing it by hand, then shell balance might be actually easier to kind of do step by step. And that's why shell balance is still a popular way to solve problems. All right. I see you on Monday.
Thank you.